All right, so we're starting into chapter 3. And we're going to talk about exponential functions. Need a pencil?
Yes, sir. Much appreciated.
Thank you.
Thank you.
All right. So along with, we've talked about polynomial functions. Chapter 2 is about polynomial functions and rational functions. So polynomial functions, rational functions. First semester we talked about trig functions. In this chapter we'll talk about exponential and logarithmic functions. Those types of functions, polynomials, rationals, trig functions, and exponential logarithmic functions are the main types of functions that we study, that we talk about in the majority of the math that we'll do. There are other types of functions, but those are the main types. Exponential functions are important because they model, they can model cell growth, they can model radioactivity, they can model population, they can model interest. So exponential functions are a really important family of functions. So what we're going to do today is start out with a definition of what an exponential function is, have an idea of what their graphs look like, and then do a little bit of work with exponential functions. So our exponential function, we're going to call our function f with a base a. So our exponential function is always going to have a base. We're going to write that as f of x equals a raised to the x power. And a is some number greater than 0, and we're saying that a doesn't equal 1, because then it's not really a very interesting function. A doesn't equal 1, and x is a real number. So this is what we're talking about when we're talking about an exponential function. We have some base that stays the same, and we're raising that base to a power. What we're going to do, so this is our function. What we're going to do is take a look at the graph of an exponential function. So we have an idea of what the graph looks like, and we'll talk about when x is positive and when x is negative, how our graph changes. So the graphs of exponential functions. A couple of things about the graphs. So we have f of x equals a to the x. Our facts about our graphs, the domain. Domain is all real numbers. So I can put any number in for x. There's no numbers give us a problem with this function. So our domain is all real numbers. The range are numbers greater than 0. So we only get positive numbers out of an exponential function. We never get a negative number. And we never get 0. Our graph is always going to have a y-intercept. If we don't do any kind of shifting, our y-intercept is going to be at the point 0, 1. So y equals 1 is our y-intercept. And that is because this was without any shift. So our function is f of x equals a to the x. Because a to the 0 equals 1 for any number. Y equals 0 is a horizontal asymptote. So our function is always greater than 0. Never gets quite reaches 0. It gets really close, but it never quite gets to 0. Our function is increasing. If a is greater than 1. So our function just gets bigger and bigger and bigger and bigger if our base is greater than 1. It never goes back down. It always goes up, up, and up, and up. Number 6, our last fact about our graph, is our function is decreasing if a is between 0 and 1. So if our base is a fraction or a decimal, then our function is decreasing. It goes down, 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 and never changes. So I'm going to sketch a graph of an exponential function just so we know what we're talking about. But this is true of any exponential function that's not shifted. Domain is all real numbers. The range, real numbers greater than 0. It's always going to have a y-intercept at y equals 1. Horizontal asymptote at y equals 0. Be increasing if our base is greater than 1, and decreasing if our base is a fraction. So let's sketch a quick graph of f of x equals 2 to the x. So our base is greater than 1, so we know that our function is going to be increasing. So if I draw a quick graph here, and it doesn't have to be perfect and beautiful. And I'll go further this way as well. So here's x and here's y. My function is going to look like this. We'll do it a little shallower. So our function is increasing. My y-intercept is at the point 0, 1. Our horizontal asymptote is y equals 0, so the x-axis. Eventually, when x gets really big, negative numbers, we get really close to 0. And if we wanted to plot some additional points here, if I plugged in x equals negative 2, if x equals negative 2, y is 2 to the negative 2, which is the same as 1 over 2 squared, or 1/4. So if x is negative 2, y is going to be 1/4. So this would be negative 2, 1/4. If x is negative 1, I'm just plotting some additional points, so y would be 2 to the negative 1, which is 1/2. So at negative 1, I'm up here at negative 1, 1/2. So that would be an additional point. And I could keep going and plot additional points. So if x is 1, y would be 2 to the first power, which is 2. So if I go here, x is 1. My point here is 1, 2. And I could plug in x equals 2. I get y equals 2 to the 2, which is 4. So if I'm at here, my point would be 2, 4. So those would be some points on my graph. So any exponential function is going to look more or less like this. And if I want to plot a decreasing exponential function where my base is a fraction. So let's say f of x equals 2 to the minus x. Now it's important to realize when I have a negative exponent, 2 to the negative x is the same as, and we did this on our worksheet the other day, 1 over 2 to the x, which is the same as 1/2 to the x power. So 2 to the negative x is the same as 1/2 to the x. So our base here, our base is 1/2, our base is less between 0 and 1. So we're going to have a decreasing function. So the graph for this one is going to look like so this is y and this is x. My decreasing function, exponential function, is going to look like this. My intercept is still going to be 0, 1, my y-intercept. And then I could plug in some additional points, just like we did up here. And we would have, if x equals -2, y equals 1/2 to the -2. And we get 4. So if x is -2, my point here would be, I know my graph isn't to scale, but this point would be 2, 4. If x is -1, y would be 1/2 to the -1, which is 2. And basically what we're doing is flipping our points around. So what was positive over here turns out to be on the negative side over here. And it would be the same for x equals 1. I would get y equals 1/2 to the first power. And that's just 1/2. So my point here is going to be 1, 1/2. And if x equals 2, I get y equals 1/2 squared, which is 1/4. So those would be some additional points on my graph. And any exponential function with a fraction as our base is going to look more or less like this. It's always going to have a y-intercept at 0, 1. The y-axis is always going to be an asymptote, and it's always going to decrease like so. I'm sorry, the x-axis. Y equals 0 is an asymptote. All right, so there's our graphs. Any questions on the basic graphs of the exponential functions? All our graphs are going to look essentially the same, just slight different changes in shape and behavior based on what our base is. All right. So our shifting exponential functions. Exponential functions shift just like polynomial functions. The rules are exactly the same. So we're not using any different rules for shifting our exponential functions. They're exactly the same. So let's look quickly if our parent function is y equals 4 to the x. So this is our parent function. What is a shift of, what is this going to do if I do 4 to the x plus 2? So how is that going to shift? So think about how we shift parabolas. If I have an x plus 2 in the parentheses, how does the parabola shift? To left 2. This is just left 2. Well, this is, I could write it like this. 4 to the x plus 2. It's the same idea. I'm adding or subtracting from the x. So that shifts left or right. And the sign is the opposite. So this just shifts left 2. So everything about the function would just shift to the left by 2 units. So if I had y equals 4 to the x plus 2 minus 3, how would that one shift? All right, can you help us out, Parker? Y equals 4 to the x plus 2 minus 3. How would that one shift? Left 2 down 3. So it's shifting just like a parabola. What if we had y equals minus 4 to the x? What would that do? Flip over the x-axis. And how about a y equals 4 to the minus x? And we just did an example of that. So how can we think of this one as a shift? Flip over the y-axis. And that's what we just looked at with the functions that we graphed. Is when we graphed 2 to the minus x, it was just flipped over the y-axis. So our functions are going to shift just like polynomial functions, exactly the same rules, nothing different. And our intercepts are going to shift. So if we shift our function down 2, our intercepts are going to shift down 2. Our horizontal asymptote is going to shift down 2. So everything shifts with the function. So questions on shifting these functions? All right, I want to talk about a couple of applications, applications of exponential functions, and then we're going to be finished. So we want to talk about the natural base. Exponential functions, there's one base for exponential functions that comes up so frequently that we give it a special name. So the number e is a lot like pi in that if we write it as a decimal, it goes on forever, it never repeats. And it's our most common base for an exponential function. E is about, if I just write an approximation, is about 2.71828, and it keeps going. We're going to use E as our base for our natural exponential function. So if we use E as our base, we say f of x equals e to the x. So e is just this number, and e comes about because this number comes up a lot when we deal with exponential functions. It was originally discovered when a gentleman was calculating compound interest and was compounding the interest more and more and more frequently. and he realized that this number comes out of calculating compound interest. And that formula, just so you know, that you'll see this again if you go further in math. We look at 1 plus x to the x power. And as x gets very large, this expression gets closer and closer to e. No. So e is like you could think of it as an asymptote. And when we talk about it in calculus, we call it's a limit. So e is the limit of this function. So it never actually gets there, but it gets very close. And this comes about from the compound interest formula that we'll talk about in just a minute. So we call e to the x the natural exponential function, and e is our natural base. So since this came about from calculating compound interest, we're going to use compound interest as a way to apply exponential functions. So let's look at compound interest. And you guys have seen this equation before, so this shouldn't be anything that's extremely new. So for our compound interest, we're going to have some terminology. A0 is, that's not what I want AN. AN is the amount that we have after some number n pay periods. And we're going to let P be the principal. And that's the amount that we start with. The amount that we start with is the amount we invest. And we're going to let R be the annual interest rate. So it'd be whatever, 15% per year, something like that. And N equals the number of pay periods per year. So this is our terminology for compound interest. I could go through the. It's not hard to come up with a formula. It just involves factoring and repeated applying interest. But rather than doing that, I think it would be more confusing to do that than if I just say what our formula is. So our formula is our amount equals our principal times 1 plus R over N raised to the N T. And T is the number, I'm going to say T is the number of years. I forgot to write that up here. So this tells us the amount that we will have if we invest our principal at interest rate R that compounds n times per year for a number of years t. And it's important to remember that R is for this formula, is the annual interest rate, and N is the number of pay periods per year. And this shouldn't be prints of PLE, it should be prints of PAL. All right, questions on our formula? So this is one application of exponential functions because our amount is some function of this exponent n times t. So let's look at some examples of calculating with the compound interest formula. So let's say we have an investment. We invest $5,000 that pays 6% annually for 10 years. We want to know how much we have how much we will get if our interest is compounded, and we're going to do several examples. For number one, we're going to compound annually. Okay, I'll just say if the interest for our first example, we want to compound annually. So my amount is, what are we plugging into our formula? What's our principal? 5,000. And we have 1 plus. What's our annual interest rate here? 6, and we want to write that as a decimal, 0.06. And n is how many times we're compounding per year. So if we're compounding annually, how many times we compound per year? 1. And we're investing for 10 years. So I have 1 times 10. Now the most common mistake that people make when they calculate this is they do the exponent before they do the parentheses. So do everything in your parentheses first, then you do your exponents, and then you do your multiplication. So remember your order of operations. And if I calculate this out, 0.06 divided by 1, add 1, raise it to the 10th power, multiply it by 5,000, you should get 8954.24. So if our interest rates compounded annually, I end up with an investment of $5,000, end up with about $8,900. For the second example, we want to compound quarterly. So my amount, my principal is still $5,000. 1 plus 0.06 is our interest rate. Compounded quarterly, how many times per year? 4. So n here is 4. Our time is still 10 years. I'm going to divide 0.06 by 4, add it to 1, raise it to the 40th power, and then multiply by 500. And you should get 9070.09. So just a little bit more money if we compound quarterly. How about, let's calculate monthly. So my principal is still 5,000. 1 plus 0.06 is still my rate. Monthly, how many times do I compound per year? 12. And I have 12 times 10. My time is still 10 years. And if I calculate that all out, 0.06 divided by 12, add 1, raise that to the 12th the 120th power, multiply by 500, and I get $9096.98. So it goes up just a little bit if I change from quarterly to monthly. And for the last one, daily, our amount is 5,000 times 1 plus 0.06 is still our rate. Daily, how many compounding periods do I have? 365. And I'm raising that to the 365 times 10th power. If I calculate that all out, you end up with $9,110.14. So we see that as our compounding period increases, the amount that we end up with increases, but it goes up more and more slowly as our compounding period increases. And this is where the number E comes in. If I keep doing this formula and I compound the interest more and more frequently, daily, hourly, minutely, every second, every fraction of a second, these numbers will go up, but they go up really slowly. And we end up with a different formula if we're compounding what we call compounding continuously. So any questions on this before I move on? Okay, so continuously compounded interest So what we're doing with continuously compounded interest is we're just increasing that compounding rate. We're increasing that n from daily, hourly, minutely, secondly, fractions of a second. And that's where our number E comes in. The more and more, then we get closer and closer to that number E. And our formula becomes A equals P e to the RT. And again, the amount, A is the amount that we have, P is our principal, R is our annual interest rate, and T is the time that we have our investment. R is annual interest rate. And T is the time in years. So if we increase the compounding, if we keep increasing the frequency of our compounding, then our formula turns into this. And this is our continuously compounded interest formula. And if we use the same numbers that we did before and compound our interest continuously, I would have A equals 5,000 times E to the 0.06 times 10. There's a button in your calculator that does E to the exponent. And if we plug this into our calculator, we would get about 9110.59. So if we compounded our interest continuously, we never stopped compounding the interest, after 10 years we'd end up with $9,110.59. So just slightly more than if we compounded daily, slightly more than if we compounded monthly, but still a little bit more. Any questions? All right, so we know a little bit about what exponential functions are. We know what their graphs look like. We know a little bit about shifting them. They follow the same rules as shifting. And we came up with a couple of applications using interest. Those are a couple of applications of exponential functions. All right, our homework. No more notes. All right, there you go.